This presentation is delivered by the Stanford Center for Professional Development.
Okay, so welcome back. And what I want to do today is talk about Newton's method, which is an algorithm for fitting models like logistic regression. And then we'll talk about exponential family distributions and generalized linear models, which is a very nice class of ideas that will tie together the logistic regression and the ordinary least squares models that we've seen. So hopefully I'll get through that today. So throughout the previous lecture and this lecture, we're starting to use increasingly large amounts of material on probability. So if you'd like to see a refresher on the foundations of probability, if you're not sure if you quite had the prerequisites for this class in terms of a background in probability and statistics, then the discussion section taught this week by the TAs will go over sort of like a review of probability. At the same discussion sections also taught by the TAs will also briefly go over sort of MATLAB and octave notation, which you need to use for your problem sets. And so if either you want to see a review of the probability and statistics prereqs, or if you want to sort of get a short tutorial on MATLAB and octave, please come to the next discussion section. All right, so just to recap briefly, towards the end of the last lecture, I talked about the logistic regression model, where we had, which was an algorithm for classification, and we had that P of y given 1, given x, P of y equals 1, given x and parameterized by theta. Under this model, right, this was 1 over 1 plus e to the negative theta transpose x. And then, you can write down the log likelihood, right, given a training set. Which was that. And by taking derivatives of this, you can derive sort of a gradient ascent rule for finding the maximum likelihood estimate of the parameters theta for this logistic regression model, right? And so last time I wrote down the learning rule for batch gradient ascent, but the version for stochastic gradient ascent, where you look at just one training example at a time, would be like this. Okay. Okay, so last time I wrote down batch gradient ascent. This is stochastic gradient ascent. So if you want to fit a logistic regression model, meaning find the value of theta that maximizes this log likelihood, gradient ascent or stochastic gradient ascent or batch gradient ascent is a perfectly fine algorithm to use. But what I want to do is talk about a different algorithm for fitting models like logistic regression. And this will be an algorithm that will, I guess, often run much faster than gradient ascent. Okay. And this algorithm is called Newton's method. And when we describe Newton's method, I'm actually going to ask you to consider a different problem first, which is, let's say you have a function f of theta, right? And let's say you want to find the value of theta so that f of theta is equal to 0. Okay, so let's start by considering this problem first, and then we'll sort of slowly change this until it becomes an algorithm for fitting maximum likelihood models like the logistic regression. So let's see. Yeah, yes, that works. Okay, so let's say that's my function f. This is my horizontal axis is theta. This is a plot of f of theta. And so we're really trying to find this value for theta, at which f of theta is equal to 0. This is a horizontal axis. So here's the algorithm I'm going to use. I'm going to initialize, theta at some value, which I call theta superscript 0. And then here's what Newton's method does. We're going to evaluate the function f at that value of theta. And then we'll compute the derivative of f, and we'll use the linear approximation to the function f at that value of theta. So in particular, I'm going to doctor my function a bit. I'm going to, I'm going to take the tangent to my function. Right, hope that makes sense. Let's doctoring the function a bit to make this work out nicely. I'm going to take the tangent to my function at that point theta 0. And I'm going to sort of extend this tangent down until it intercepts the horizontal axis. I'm going to see what value this is. And I'm going to call this theta 1. Okay? And so that's one iteration of Newton's method. And what I'll do then is the same thing. Look at this point. Take the tangent down here. And that's 2 iterations of the algorithm. And then you sort of keep going. That's theta 3, and so on. Okay? So let's just go ahead and write down what this algorithm actually does. So to go from theta 0 to theta 1, let me call, that length, let me just call that capital delta. So if you remember the definition of a derivative, right? The derivative of f evaluated at theta 0, in other words, the gradient of this first line, by the definition of gradient, this is going to be equal to this vertical length divided by this horizontal length. The gradient of this, so the slope of this function, is defined as the ratio between this vertical height and this width of the triangle. And so that's just equal to f of theta 0 divided by delta, which implies that delta is equal to f of theta 0 divided by f prime of theta 0. Okay? And so theta 1 is therefore theta 0 minus delta, minus the capital delta, which is therefore just f of theta 0 over f prime of theta 0. Right? And more generally, one iteration of Newton's method proceeds as theta t plus 1 equals theta t minus f of theta t divided by f prime of theta t. Okay? So that's one iteration of Newton's method. Does that make sense? Now, this is an algorithm for finding a value of theta for which f of theta equals 0. So we can apply the same idea to maximizing the log likelihood, right? So we have a function L of theta, and we want to maximize this function. Well, how do you maximize the function? You set its derivative to 0, right? So we want theta such that L prime of theta is equal to 0. Right? So to maximize this function, we want to find a place where the derivative of this function is equal to 0. And so we just apply the same idea. And so we get theta t plus 1 equals theta t minus L prime of theta t over L double prime of t. L double prime of theta t, okay? Because to maximize this function, we just let f be equal to L prime. Let f be the first derivative of L, and then we want to find the value of theta for which the derivative of L is 0, and therefore it must be a local optimum. Okay. So. Does this make sense? The question is about this? Yeah.
What are the conditions of f for the method to work?
the answer to that is fairly complicated. There are conditions on F that will guarantee that this will work. They're fairly complicated, and this is more complex than I want to go into now. In practice, this works very well for logistic regression, and for sort of generalized linear models I'll talk about later. Yeah.
Selection of theta 0 is how to initially the starting point.
Yeah, it usually doesn't matter. When I implement this, I usually just initialize theta 0 to the vector, to just initialize the parameters to the vector of all zeros, and usually this works fine. It's usually not a huge deal how you initialize theta. Yeah, last question?
So, without getting into how when it converges, is it more likely to converge or less likely to gradient descent, or is it just different situations?
Yeah, let me say some things about that. They'll sort of answer it. Yeah, all of these algorithms, tend not to have convergence problems, and all of these algorithms will generally converge, unless you choose too large a learning rate for gradient ascent or something. But the speeds of convergence of these algorithms are very different. So, it turns out that Newton's method is an algorithm that enjoys extremely fast convergence. The technical term is that it enjoys a property called quadratic convergence. Don't know about what that means, but just stated informally, means that asymptotically, every iteration of Newton's method will double the number of significant digits that your solution is accurate to. Okay, so just up to constant factors, right? Suppose that on a certain iteration, your solution is within 0.01 of the optimum, so you have 0.01 error. Then after one iteration, your error will be on the order of 0.001. And after another iteration, your error will be on the order of 0.0001. Okay, so this is called quadratic convergence because you essentially get to square the error on every iteration of Newton's method. Caveats that this is an asymptotic result that holds only when you're pretty close to the optimum anyway. So this is a theoretical result that sort of is true, but because of constant factors and so on, may paint a slightly rosier picture than might be accurate. But in practice, when you implement, when I implement Newton's method for logistic regression, usually it converges in like a dozen iterations or so for most reasonable sized problems of tens or hundreds of features. So one thing I should talk about, which is what I wrote down over there, was actually Newton's method for the case of theta being a single row number. The generalization to Newton's method for when theta is a vector rather than when theta is just a row number is the following, which is that theta t plus 1 is theta t plus, and then we had the second derivative divided by the first derivative divided by the second derivative. And the appropriate generalization is this, where this is the usual gradient of your objective, and H here is a matrix called the Hessian. This is just the matrix of second derivatives where Hij equals. Okay, so just instead of the first derivative divided by the second derivative, now you have a vector of first derivatives times the inverse of the matrix of second derivatives. So this is sort of just the same thing, but written out for multiple dimensions. So for logistic regression, again, usually for a reasonable number of features in training examples, when I run this algorithm, it usually converges. Usually you see a conversion anywhere from sort of 3 iterations to like a dozen or so iterations. So compared to gradient descent, this usually needs far fewer iterations to converge. compared to gradient descent, let's say batch gradient descent, the disadvantage of Newton's method is that on every iteration, you need to invert the Hessian. Right? And so the Hessian will be an n by n matrix, or an n plus 1 by n plus 1 dimensional matrix, if n is the number of features. And so if you have a large number of features in your learning problem, if you have tens of thousands of features, then inverting H could be a slightly computationally expensive step. But for smaller, more reasonable numbers of features, this is usually a very fast algorithm. This question?
Is the minus sign for the scalar case and the plus sign for the matrix case? Is there a...
Oh, yes, you're right. Let's see. I think you're right. That should probably be a minus. Do you want to tell? Yeah, thanks. Yeah, thanks. Should be a minus. Right. Okay. And actually, I invite you to think about the following problem also. I wrote down this algorithm to find the maximum likelihood estimate of the parameters for logistic regression. Right? So I wrote down this, for maximizing a function. So I'll leave you to think about this yourself. If I wanted to use Newton's method to minimize a function, how does the algorithm change? Right? So I'll leave you to think about that. Okay? So I wrote this down for maximization. So how does the algorithm change if you want to use it for minimization? Okay, say again? Yeah. Actually, actually, the answer is that it doesn't change. I'll leave you to work that out yourselves why. Okay. All right. Let's talk about generalized linear models. And let me just to give a recap of both of the algorithms we talked about so far. We talked about two different algorithms for modeling P of y given x and parameterized by theta. Right. In one of them, R was a real number, and we assumed that, and we saw that if we assume it has a Gaussian distribution, then we got, ordinary least squares, linear regression. In the other case, we saw that if was a classification problem where y took on the value of either 0 or 1. In that case, what's the most natural distribution over zeros and ones is the Bernoulli. Right? Bernoulli distribution models random variables with two values. And in that case, we got logistic regression. Okay. So along the way, some of the questions that came up were, for logistic regression, where on earth did I get the sigmoid function from? Right? And so there are actually other choices you can use for, so just where did this function come from? And there are other functions that could have plugged in, but the sigmoid function turns out to be a particularly natural default choice that led us to logistic regression. And what I want to do now is take both of these algorithms and show that there are special cases of the broader class of algorithms called generalized linear models, and it'll be part of this broader. It'll be as part of this broader class of algorithms that things like the sigmoid function will fall out very naturally as well. So let's see, something along the piece of chalk. Okay. I should warn you, the ideas in generalized linear models are somewhat complex. So what I'm going to do today is try to sort of point out the key ideas and give you a gist of the entire story. And then some of the details in the math and the derivations, I'll leave you to work through by yourselves in the lecture notes which post online. Okay. Okay. So let's start by considering these two distributions, the Bernoulli and the Gaussian. Right? So suppose we have data that is 0, 1 valued, and we want to model it with, a Bernoulli random variable parameterized by phi. Right. So the Bernoulli distribution has that the probability of y equals 1 is just equal to phi, right? So the parameter phi in the Bernoulli specifies the probability of y being 1. Now, as you vary the parameter theta, you get, you sort of get different Bernoulli distributions. As you vary the value of theta, you get different probability distributions on y. that have different probabilities of being equal to 1. And so I want you to think of this as not one fixed distribution, but as a set or as a class of distributions that you get as you vary theta. Okay? And in the same way, if you consider Gaussian distribution, as you vary mu, you will get different Gaussian distributions. So think of this again as a class or as a set of distributions. And what I want to do now is show that both of these are special cases of a class of distributions called the exponential family distribution. And in particular, we'll say that the class of distributions, like the Bernoulli distributions that you get as you vary theta, we'll say that the class of distributions is in the exponential family if it can be written in the following form. P of y parameterized by theta is equal to B of y minus A of theta. Okay. Let me just give some of these terms names, and then well, I'll say a bit more about what this means. So eta is called the natural parameter of the distribution, and T of y is called the sufficient statistic. Usually, for many of the examples we'll see, including the Bernoulli and the Gaussian, T of y is just equal to y. So for most of this lecture, you can mentally replace T of y to be equal to y. This won't be true for the very final example we do today, but mentally you think of T of y as equal to y. And so for a given choice of these functions, a, b, and t, right? So let's say I fix the forms of the functions a, b, and t. Then this formula defines, again, a set of distributions. So defines a class of distributions that's now parameterized by eta. Okay, so again, let's say you write down specific formulas for a, b, and t. Right? So choose specific choices of a, b, and t. Then, as I vary eta, I get different distributions. Again, and I'm going to show that the Bernoulli, I'm going to show that the Bernoulli and the Gaussians are special cases of exponential family distributions, and by that I mean that I can choose specific functions a, b, and t, so that this becomes the formula of the distribution of either a Bernoulli or a Gaussian. And then again, as I vary eta, I'll get Bernoulli distributions with different means, or as I vary eta, I'll get Gaussian distributions with different means for my fixed values of a, b, and t. Okay. And for those of you that know what a sufficient statistic in statistics is, T of y actually is a sufficient statistic in the formal sense of a sufficient statistics for a probability distribution that you may have seen in a statistics class. If you don't know what a sufficient statistic is, don't worry about it. We sort of don't need that property today. Okay. So, one last comment. Right. Often T of y is equal to y, and in many of these cases, eta is also just a real number. So in many cases, the parameter of this distribution is just a real number, and eta transpose T of y is just a product of real numbers. So again, that'll be true for our first two examples, but not for the last example I'll do today. So now let's show that the Bernoulli and the Gaussian are examples of exponential family distributions. We'll start with the Bernoulli. So the Bernoulli distribution with parameter phi, well, I guess I wrote this down already. P of y equals 1 parameterized by phi is just equal to phi. Right? So the parameter phi specifies the probability that y equals 1. And so my goal now is to choose T, A, and B. Let's choose A, B, and T so that my formula for the exponential family becomes identical to my formula for the distribution of a Bernoulli. Okay. So, probability of y parameterized by phi is equal to that, right? And you already saw there's a similar exponential notation when we talked about logistic regression, right? The probability of y being 1 is phi. The probability of y being 0 is 1 minus phi. And so we can write this compactly as phi to the y times 1 minus phi to the 1 minus y. So I'm going to take the exponent of the log of this. And exponentiation and taking logarithms cancel each other out, right? So it doesn't change anything. And this is equal to e to the y And so, I'm going to define that to be eta, this to be t of y, and this will be minus a of eta. And then b of y is just 1, so b of y doesn't matter. Okay. So, just take a second to look through this and make sure it makes sense. I'll clean another board while you do that. So let me just write down a few more things. Just copying from the previous board, we had that eta is therefore equal to log phi over 1 minus phi. It turns out, so if I won't do the algebra, it turns out if you just take this formula and if you invert it, if you solve for phi, if you solve for eta as a function of phi, or just do the algebra, solve for eta as a function of phi, just invert this formula, you find that phi is 1 over 1 plus eta minus eta. Okay? And so somehow the logistic function magically falls out of this. And we'll take this even further later. Again, copying definitions from the board from the previous board, a of eta, I said, is minus log of 1 minus phi. Right? So again, phi and eta are functions of each other, right? So eta depends on phi, and phi depends on eta. So if I plug in this definition for eta, into this, plug in this definition for phi into that, I'll find that a of eta is therefore equal to log 1 plus e to the eta. Again, this is just algebra. This is not terribly interesting. And just to complete, and just to complete the rest of this, t of y is equal to y, and b of y is equal to 1. Okay? So just to recap what we've done, we've come up with a certain choice of functions a, t, and b, so that my formula for the exponential family distribution now becomes exactly the formula for the distribution, so for the probability mass function of the Bernoulli distribution. Okay, and the natural parameter eta has a certain relationship with the original parameter of the Bernoulli. Question?
Go from the second last line to the last line.
Let's see. From which line to which line?
The second to the last line.
Oh, this line to this line. Let's see. Yeah, so this is, well, expand this term out, 1 minus y times log 1 minus phi. And so 1 times log 1 minus phi becomes this. And the other term is minus y times log 1 minus phi. And then, so the minus of a log is log 1 over x, right? Is log 1 over whatever. So minus y times log 1 minus phi becomes sort of y times log 1 over 1 minus phi. Does that make sense? Yeah. Cool. Anything else? Yeah. Yes.
Now eta is a scalar, isn't it?
Up
there, it's
yes.
Eta transpose, so it can be a vector or.
Yes, that's right. So let's see. In this and the next example, eta will turn out to be a scalar, and so, well, on this board. And so if eta is a scalar and t of y is a scalar, then this is just, a real number times a real number. So this would be like a one-dimensional vector transpose times a one-dimensional vector. And so this is just real number times real number. Towards the end of today's lecture, we'll go over just one example where both of these are vectors. But for many distributions, these will turn out to be scalars. Yeah. Oh,
I'm not sure, like, does the Bernoulli distribution, I'm not sure how that's a distribution, P, Y, phi, because, it doesn't have the zero probability for stuff other than 0 and 1.
I see. So, yeah, let's for this, let's imagine that we're restricting the domain of the domains of the input of the function to be y equals 0 or 1. So think of that as maybe an implicit constraint on this. I could write it down and make it more explicit. But so this is a probability mass function for y equals 0 or y equals 1. So, and write down y equals 0, 1. Let's think of that as an implicit constraint. So, cool. Let me now also, so this takes a Bernoulli distribution and writes in the form of an exponential family distribution. Let me also just do that very quickly for the Gaussian. I won't do the algebra for the Gaussian, but I'll basically just write out the answer. So, right, well, right, with a normal distribution with mean mu and variance sigma squared. And so you remember, was it 2 lectures ago when we're deriving the maximum likelihood, just the previous lecture, when we were deriving the maximum likelihood estimate for the parameters of ordinary least squares, right? We showed that the parameter for sigma squared didn't matter. So when we derived a probabilistic model for least squares regression, we said that no matter what sigma squared was, we end up with the same value of the parameters. So for the purposes of just writing less in today's lecture and not taking into account sigma squared, I'm just going to set sigma squared to be equal to 1. Okay, so as to not worry about it. Lecture notes talks a little bit more about this, but I'm just going to just to make what I'm doing in class a bit easier and simpler today. Let's just set sigma squared equals 1. This is sigma squared is essentially just a scaling factor on the variable y. So in that case, the Gaussian density is given by this. 1 minus mu squared. And, well, via a couple of steps of algebra, which I'm not going to do, but it's written out in full in the lecture notes you can download. This is 1 over root 2 pi e to the minus 1/2 y squared times e to the mu y minus 1/2 mu squared. Okay, so I'm just not doing the algebra. And so that's b of y. We have mu of is equal to eta. T of y equals y. And, well, a of eta is equal to minus 1/2. Actually, oh, I think it should actually be plus 1/2. Did I get that right? No, sorry. Let's see, excuse me, plus sign there. Okay, should be minus 1/2 mu squared. And because mu is equal to eta, this is just minus 1/2 eta squared. Okay? And so this would be a specific choice again of A, B, and T that expresses the Gaussian density in the form of an exponential family distribution. And in this case, the relationship between mu and eta is that mu is just equal to eta. So the mean of the Gaussian is just equal to the natural parameter of the exponential family distribution. Oh, this is minus all? Oh, okay, fine, thanks. And so, no, I'm guessing that should be plus then. Is that right? Okay. Oh, yes, you're right. Thank you. Yeah. Right. And so it actually turns out that if you've taken like an undergrad statistics class, it turns out that most of the, quote, textbook distributions, not all, but most of them, can be written in the form of an exponential family distribution. So you saw, the Gaussian, the normal distribution. It turns out the multivariate normal distribution, which is a generalization of Gaussian random variables, right, to higher dimensions, to vectors. The multivariate normal distribution is also an exponential family. You saw the Bernoulli is an exponential family. It turns out the multinomial distribution is too, right? So the Bernoulli models outcomes over, 0 and 1, over coin tosses with 2 outcomes. The multinomial models outcomes over k possible values. That's also an exponential family distribution. You may have heard of the Poisson distribution. So the Poisson distribution is often used for modeling counts, things like the number of radioactive decays in the sample, or the number of customers to your website, the number of visitors arriving in the store. The Poisson distribution is also an exponential family. So are the gamma and the exponential distributions, if you've heard of them. So the gamma and the exponential distributions are distributions over positive numbers, right? And so they're often used to model intervals. Like if you're standing in the bus stop and you want to ask, when is the next bus likely to arrive? How long do I have to wait for my bus to arrive? Often you model that with sort of gamma distributions or exponential families, or exponential or the exponential distribution. Those are also an exponential family. Even more esoteric distributions like the beta and the Dirichlet distributions. These are probability distributions over fractions, or really probability distributions over probability distributions. And also things like the Wishart distribution, which is a distribution over covariance matrices. So all of these, it turns out, can be written in the form of exponential family distributions. In the problem set, we actually ask you to take one of these distributions and write it in the form of the exponential family distribution and derive a generalized linear model for it. Okay? Which brings me to the next topic of having chosen an exponential family distribution, how do you use it to derive a generalized linear model? Right. So, generalized linear models are often abbreviated GLMs. And I'm going to write down the 3 assumptions. You can think of them as assumptions. You can think of them as design choices that will then allow me to sort of turn a crank and come up with a generalized linear model. So the first one is I'm going to assume that, given my inputs x and my parameters theta, I'm going to assume that the variable y, the output y, or the response variable y I'm trying to predict, is distributed exponential family with some natural parameter eta. Okay, and so this means that there is some specific choice of those functions a, b, and t, so that the conditional distribution of y given x and parameterized by theta is exponential family with parameter eta, where here eta may depend on x in some way. Okay, So for example, if you're trying to predict, if you want to predict how many customers will arrive at your website, right? You may choose to model the number of people, the number of hits on your website via a Poisson distribution, since Poisson distribution is natural for modeling account data. And so you may choose the exponential family distribution here to be the Poisson distribution. I'm going to assume that given x, our goal is to output the expected value of y given x. Okay, so given the features in the website example, so given a set of features about whether there were any promotions, whether there were sales, how many people linked to your website or whatever, I'm going to assume that our goal in a machine learning problem is to estimate the expected number of people that will arrive at your website on a certain on a given day. So in other words, I'm saying that I want h of x, right, to be equal to, oh, excuse me, I actually meant to write t of y here. My goal is to get my learning algorithms hypothesis to output the expected value of t of y given x. But again, for most of the examples, t of y is just equal to y. And so for most of the examples, our goal is to get our learning algorithm to output the expected value of y given x, because t of y is usually equal to y. Yeah. Oh yes, same thing, right. T of y is a sufficient statistic. Same t of y. And lastly, this last one, I wrote down these are assumptions. This last one, you might maybe want to think of this as a design choice, which is, so if up here I assume that the distribution of y given x is distributed, exponential family with some parameter eta, right? So the number of visitors in my website on any given day will be Poisson with some parameter eta. And the last decision I need to make is, what's the relationship between my input features and this parameter eta, parameterizing my Poisson distribution or whatever. And this last step, I'm going to make the assumption, already a design choice, that I'm going to assume the relationship between eta and my features x is linear, and in particular that they're governed by this, that eta is equal to theta transpose x. Okay? And the reason I make this design choice is it will allow me to turn the crank of the generalized linear models machinery and come up with some very nice algorithms for fitting, say, Poisson regression models, or perform regression with a gamma distribution outputs or exponential distribution outputs and so on. So, let's work through an example. Excuse me. And, right, eta equals theta transpose x works for the case where eta is a real number. For the more general case, we would have eta I equals theta I transpose x if, eta is a vector rather than a real number. But again, most of the examples, eta would just be a real number. Okay. All right. So let's work through the Bernoulli example. We assume y given x parameterized by theta. This is distributed exponential family with natural parameter eta. And for the Bernoulli distribution, I'm going to choose, A, B, and T to be the specific forms that cause this exponential family to become the Bernoulli distribution, right? So this is the example we worked through just now, the first example we worked through just now. So, and we also have, so for fixed, so for any fixed value of x and theta, right? My hypothesis, my learning algorithm will make a prediction, or will sort of output h of x, right? Which is by, my I guess assumption number 2. I want my learning algorithm to output the expected value of y given x and parameterized by theta. When y can take on only the values 0 and 1, then the expected value of y is just equal to the probability that y is equal to 1. Right, so the expected value of a Bernoulli random variable is just equal to the probability that is equal to 1. And so, the probability that y equals 1 is just equal to phi, because that's the parameter of my Bernoulli distribution, right? Phi is, so by definition, I guess, is the probability of my Bernoulli distribution and the value of 1. Which we worked out previously. Phi was 1 over 1 plus e to the negative eta. So we worked this out on a previous board. This is the relationship. So when we wrote down the Bernoulli distribution in the form of an exponential family, right, we worked out what the relationship was between phi and eta, and it was this. So we worked out what the relationship between the expected value of y and eta. It was this relationship. And lastly, because we made the design choice or the assumption that eta and theta are linearly related. This is therefore equal to 1 over 1 plus e to the minus theta transpose x. Okay? And so that's how I come up with the logistic regression algorithm when you have a variable y, when you have a target variable y, or also call it response variable y, that takes on 2 values and that you choose to model via a Bernoulli distribution. Okay? Do each of the steps make sense? You raise your hand if this makes sense. Yeah, okay, cool. Right. So I hope you get the ease of use of this, also the power of this, right? The only decision I made was really, I said, why, let's say I have a new machine learning problem, and I'm trying to predict the value of a variable y that happens to take on 2 values. Then the only decision I need to make is I chose Bernoulli distribution. I said I want to model, I want to assume that given x and theta, I'm going to assume y is distributed Bernoulli. Right? That's the only decision I made. And then everything else follows automatically from having made the decision to model y given x and parameterized by theta as being Bernoulli. Okay? In the same way, you can choose a different distribution. You choose y as Poisson, or y as gamma, or y as whatever, and follow a similar process and come up with a different model, a different learning algorithm. Come up with a different generalized linear model for whatever learning problem you're faced with. A tiny bit more notation. The function g that relates g of eta, that relates the natural parameter to the expected value of y, right, which in this case is 1 over 1 plus e to the minus eta. This is called the canonical response function. And g inverse is called the canonical link function. Okay, these aren't a huge deal. I won't use this terminology a lot. I'm just mentioning this in case you hear about people talk about generalized linear models. If they talk about canonical response functions or canonical link functions, just so you know, there's all of this. Actually, many texts actually use the reverse, where this is g inverse and this is g, but this notation turns out to be more consistent with other algorithms in machine learning. So I'm going to use this notation, but I probably won't use the terms canonical response functions and canonical link functions in lecture a lot. So just, I don't know, I'm not big on memorizing lots of names of things. I'm just tossing those out there in case you see it elsewhere. Okay. For time. You know what? I think, yeah, in the interest of time, I'm going to skip over the Gaussian example. But again, just like I said, I choose Bernoulli. Why is Bernoulli, you know, go for the derivation, I get out logistic regression. You can do the same thing with the Gaussian distribution and end up with sort of the ordinary least squares model. The problem with Gaussian is almost so simple that when you see it for the first time, it's sometimes more confusing than the Bernoulli model because it looks so simple. It looks like it has to be more complicated. So let me just skip that and leave you to read about the Gaussian example in the lecture notes. And what I want to do is actually go through a more complex example. Oh, what's the question? Oh, okay, right. So how do you choose what theta will be? Right. So let me get to that at the end. So what you have there is the logistic regression model, which is a probabilistic model that assumes the probability of y given x is given by a certain form. And so what you do is you can write down the log likelihood of your training set and find the value of theta that maximizes the log likelihood of the parameters. Does that make sense? So I'll say that again towards the end of today's lecture. But for logistic regression, the way you choose theta is exactly maximum likelihood as we worked out sort of, you know, I guess in the previous lecture, using Newton's method or gradient descent or whatever. But I'll sort of try to do that again for one more example towards the end of today's lecture. So what I want to do is actually use the remaining, I don't know, 19 minutes or so of this class to go through one of the more it's probably the most complex example of a generalized linear model that I've used. And this one I want to go through because it's a little bit trickier than many of the other textbook examples of generalized linear models. So again, you know, what I'm going to do is go through the derivation reasonably quickly and give you the gist of it. And if there's steps I skipped or details that are omitted, I'll leave you to read about them sort of more carefully in the lecture notes. Okay? And what I want to do is talk about the multinomial. Okay? And the multinomial is the distribution over, you know, let's say k possible outcomes. And imagine you now have a machine learning problem where the value y that you're trying to predict can take on k possible outcomes, so rather than only 2 outcomes. Right? So obviously, so examples will be if you want to have a learning algorithm automatically send emails for you into your right email folder, and you may have a dozen email folders you want your algorithm to classify emails into. Or, you know, instead of predicting if a patient either has a disease or does not have a disease, which was a binary classification problem, if you think the patient may have one of k diseases and you want to have a learning algorithm figure out which one of k diseases your patient has and so on. So there are lots of multi-class classification problems where you have more than 2 classes. You model that with multinomial. And you know, eventually, well, so for logistic regression, I had pictures like these, right, where you have training set and you find a decision boundary that separates them. For the model I'm going to talk about, we're going to entertain the value of predicting taking on multiple values. So you now have 3 classes, and the learning algorithm will learn, you know, some way to separate out 3 classes or more rather than just 2 classes. Okay? So let's write the multinomial in the form of an exponential family distribution. So the parameters of a multinomial are phi1, phi2, up to phi k. I'll actually change this in a second. Where the probability of y equals I is phi I, right? Because there are now k possible outcomes. But if I choose this as my parameterization of the multinomial, then my parameters are actually redundant because if these are probabilities, then they have to sum up to 1. And therefore, for example, I can derive, you know, the loss parameter phi k as 1 minus, you know, phi 1 up to phi k minus 1. Right? So this would be a redundant parameterization from a multinomial. This is also called over-parameterized. And so for the purposes of this derivation, I'm going to treat my parameters of my multinomial as phi1, phi2 up to phi k minus 1. And I won't think of phi k as a parameter. I'll just, so my parameters are I just have k minus 1 parameters parameterizing my multinomial. And sometimes I write phi k in my derivations as well, and you should think of phi k as just a shorthand for this, for 1 minus the rest of the parameters, okay? So, turns out the multinomial is one of the few examples where t of y is one of the examples where t of y is not equal to y. So in this case, y is one of k possible values, and so t of y will be defined as follows: t of 1 is going to be a vector with a 1 and zeros everywhere else. T of 2 is going to be a 0, 1, 0, and so on, except that these are going to be k minus 1 dimensional vectors. Okay? And so t of k minus 1 is going to be 0, 0, 0, 1, and t of k is going to be the vector of all zeros. Okay? So this is just how I'm choosing to define t of y to write down the multinomial in the form of an exponential family distribution. Okay. Again, these are k minus 1 dimensional vectors. So this is a good point to introduce one more useful piece of notation, which is called indicator function notation. So I'm going to write 1 and then curly braces. And if I write a true statement inside, then the indicator of that statement is going to be 1. And if I write 1 and then I write a false statement inside, then the value of this indicator function is going to be a 0. So for example, if I write indicator 2 equals 3, then clearly that's false, and so this is equal to 0. Whereas indicator 1 plus 1 equals 2, I wrote down a true statement inside, and so the indicator of the statement is equal to 1. So the indicator function is just a very useful notation for indicating the truth or falsehood of the statement inside. And so, let's just do this here. To combine both of these, right, if I carve out a bit of space here. So if I use, so ty is a vector, right? Y is one of k values, and so ty is one of these k vectors. If I use ty subscript I to denote the ith element of the vector ty, okay, then ty, the ith element of the vector ty, is just equal to indicator for whether y is equal to I. Okay, so let's take I'll clean a couple more boards. Take a look at this for a second and make sure you understand make sure you understand all that notation and why this is true. Raise your hand if this equation makes sense to you. Most of you, not all. Okay. I'll just say this one. Let's see. So, well, just as one concrete example, suppose y is equal to 1. Right. Actually, sorry. Let's say. Let me see. Fine. Suppose y is equal to 1, right? So ty is equal to this vector. And therefore, the first element of this vector will be 1, and the rest of the elements will be equal to 0. Right? And so, let me try that again, sorry. Let's say I want to look at the ith element of the vector ty, and I want to know, is this 1 or 0? Right? Well, this will be 1. You know, the ith element of the vector ty will be equal to 1 if and only if y is equal to I. Because, for example, if y is equal to 1, then only the first element of this vector will be 0. If y is equal to 2, then only the second element of the vector will be 0, and so on. So the question of whether or not, whether the ith element of this vector ty is equal to 1 is answered by just asking, is y equals to I? Okay? All right. Yeah, if still not quite sure why that's true, go home and think about it a bit more. And I think and take a look at the lecture notes as well. Maybe that'll help. Just for now, let me just take my word for it. So let's go ahead and write out the distribution for the multinomial in an exponential family form. So P of y is equal to phi 1 indicator y equals 1 times phi 2 indicator y equals 2 up to phi k times indicator y equals k, right? And again, phi k is not a parameter of the distribution. Phi k is a shorthand for 1 minus phi 1 minus phi 2 minus the rest. And so, using this equation on the left as well, I can also write this as phi 1 times ty1 phi 2 ty2 dot 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 phi k minus 1 ty k minus 1 times phi k, and then 1 minus sum from that should be j. And it turns out it takes several steps of algebra that I don't have time to show. It turns out you can simplify this into, well, the exponential family form. Where eta is a vector This is a k minus 1 dimensional vector, and well, okay. So deriving this is a few steps of algebra that you can work out yourself, but I won't do here. And so using my definition for ty and by choosing eta a and b this way, I can take my distribution for a multinomial and write it out in the form of an exponential family distribution. Okay. It turns out also that, let's see, so when we worked out the Bernoulli distribution, right, one of the things we did was we also had eta as a function of phi, and then we inverted that to write out phi as a function of eta. So it turns out you can do that as well. So this defines eta as a function of the multinomial distribution's parameters phi. So you can take this relationship between eta and phi and invert it and write out phi as a function of eta. And it turns out you get that phi I is equal to e to the 8, excuse me, and you get that phi I is equal to e to the 8th I of 1 plus that. Okay. And the way you do this is you just, this defines eta is a function of phi. So if you take this and solve for eta, you end up with this. And there are a couple of steps of algebra that I'm just not showing. And then lastly, using our assumption that the etas are a linear function of the input x's, phi I is therefore equal to e to the theta I transpose x divided by 1 plus sum over j equals 1 to k minus 1 e to the theta j transpose x. Okay, and this is just using the fact that eta I equals theta I transpose x, which was one of our earlier design choice for generalized linear models. So we're just about done, and so my learning algorithm, h subscript theta of x, I'm going to think of it as outputting the expected value of ty given x and parameterized by theta. So, ty, right, was this vector of indicator functions, right? So t1 was indicator y equals 1 down to indicator y equals k minus 1. Right, so I want my learning algorithm to output this, the expected value of this vector of indicator functions. But, the expected value of indicator y equals 1 is just the probability that y equals 1, which is given by phi 1. Right, so I have a random variable that's 1 whenever y is equal to 1 and 0 otherwise. So the expected value of that, of this indicator y equals 1 is just the probability that y equals 1, which is given by phi 1. And therefore, by what we worked out earlier, this is therefore e to the theta 1 transpose x over, well, okay. And so my learning algorithm will output the probability that y equals 1, y equals 2, up to y equals k minus 1. And these probabilities are going to be parameterized by, these functions like these. Okay? And so just to give this algorithm a name, this algorithm is called Softmax regression. And is widely thought of as the generalization of logistic regression, which is regression with two classes. It's widely thought of as a generalization of logistic regression to the case of k classes rather than two classes. And so just to be very concrete about what you do, right? So you have a machine learning problem, and you want to apply softmax regression to it. So just work through the entire derivation instead of edges. I think the question you had as well about how to fit parameters. So let's say you have a machine learning problem, and y takes on one of k classes. What you do is you sit down and say, okay, I want to model y as being distributed multinomial given any x and theta. And so you chose multinomial as the exponential family. Then you sort of turn the crank. Then everything else I wrote down follows automatically from your having made the choice of using a multinomial distribution as a choice of exponential family. And then what you do is you then have this training set, right? IYI, up to XM YM, right? So you're given a training set where now each of the values of Y takes on one of K possible values. And what you do is you then find the parameters of the model by maximum likelihood. So you write down the likelihood of the parameters and you maximize the likelihood, right? So what's the likelihood? Well, the likelihood, as usual, is the product over your training set of P of Yi given Xi parameterized by theta, right? That's the likelihood, same as we had before. And that's product from product of your training set of, let me write this down now, Yi equals 1 times phi 2 of indicator, Yi equals 2, dot, 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 up to phi k of indicator Yi equals k, where, for example, phi 1 depends on theta through this formula, is e to the theta 1 transpose x over 1 plus sum over j. Well, that formula I had just now. Okay? And so phi 1 here is really a shorthand is for this formula, and similarly for phi 2 and so on, up to phi k, where phi k is 1 minus all of these things. All right? So this is I don't know, and this formula looks more complicated than it really is. What you really do is you write this down, then you take logs, compute the derivative of this formula with respect to theta, right, and apply, say, gradient ascent to maximize the likelihood. Yeah, Alex?
What are the rows of theta? But before theta has just been a vector, right? And now it looks like it's two-dimensional?
Oh, yeah. In the notation I've been using, I think of theta 1 through theta k minus 1. I've been thinking of each of these as an n or n plus 1 dimensional vector. If x is n plus 1 dimensional, then I've been thinking. So I'm thinking of you have a set of parameters comprising k minus 1 vectors, and each of these is you could group all of these together in a matrix, but I just haven't been doing that. I've been thinking of that there are sort of k minus 1 parameter vectors.
Like intuitively, what do they correspond to?
I don't know. Let's maybe sort of out of time. Let me take that offline. It's hard to answer in the same way that for logistic regression, what does theta correspond to in logistic regression? You can sort of answer that, but it's sort of.
Yeah, it's kind of like the weights for each feature.
Yeah, so similar interpretation, but maybe a bit. Yeah, it's good. Yeah, I think are there any? I'm running a little bit late. Won't we officially close for the day? But you can come up if you have more questions and take them offline. Okay, thanks.